I hope you're having a great Envirothon. My name is Ben Burpee. I am an applied limnologist, meaning that I study lakes and reservoirs and lake ecosystems for a living. I work at Ecosystem Consulting Service in Coventry, Connecticut, so we're just down the road from you guys. And today I'm going to be discussing climate change impacts on New England lakes and reservoirs. Just to quickly recap what we're going to be touching upon in today's talk, we're going to look at lake and reservoirs. We're going to do a quick review of how they work, how they behave throughout the seasons. We'll then move on to climate change in New England, just looking at current trends. Then we'll try to tease apart this question about how climate change is affecting New England lake and reservoir ecosystems. So what are the ecological responses that we're seeing in those aquatic ecosystems? And next, we'll just touch upon policy and management measures. So what measures are being conducted to maintain high water quality or to maintain healthy ecosystems in the face of a changing climate? To quickly review, this slide represents a typical seasonal lake progression. So the figure is taken from the Lake George Association in New York. So therefore it's representative of a typical temperate lake like you would see in Connecticut. We'll start at the top left corner and we'll work our way around clockwise. So in summer, days are longer and warmer, and so lakes absorb radiative energy from the sun. And as the surface of the lake absorbs that energy and warms up, it will become less dense than the colder water lying underneath it. So this warmer water essentially floats on top of the colder water, creating what we call thermal stratification. So during summer, we find lakes have these three distinct layers of water. So the warm epilimnion on the top, the cold hypolimnion on the bottom, and the transition in between these depths called the thermocline, or sometimes called the metalimnion. Thus, if you were to dive into a deep lake during peak summer and swim straight to the bottom, you would experience a temperature change similar to the inset graph in the top left-hand corner, where you would swim through the warm water, then suddenly it would get markedly colder, and you would feel that. So it's important to note here that the temperature and density differences between these layers in the top behave somewhat as a boundary. So water is circulating and mixing within the top epilimnion layer, and same in the hypolimnion layer, but these layers are not mixing together. So this means you can have very different physical and chemical conditions in the top of the lake versus the bottom of the lake. In autumn, temperatures will cool. The top of the lake will lose its heat until temperature in the upper water column is close to the temperature in the lower water column. So at this point, the thermal stratification weakens, which means the temperature-dependent density of the upper lake and bottom of the lake are close enough to mix with each other. We call this event autumn turnover. It's when the lake mixes completely and there's no longer a temperature difference between the top and the bottom. Stratifies in winter as well. You'll notice that this time, however, the warmer water is on the bottom of the lake and the colder water is on top. So this phenomenon is due to the unique temperature-dependent density property of water, where water is most dense at 4 degrees Celsius. So that means that water warmer than 4 degrees Celsius is less dense and more buoyant, and it means that water less than 4 degrees Celsius is less dense and more buoyant. So colder water floats on top of 4-degree water, as does water in its solid crystallized form, as does ice, basically, is what I'm saying. So again, 4-degree water will always sink due to its density. Therefore, you'll notice in this cartoon of a lake, 4-degree water is always on the bottom. And I circled those in red so you can see. So in spring, when the ice melts and the surface warms to 4 degrees Celsius, you'll also get a mixing event. So many temperate lakes mix twice a year, right? Once in spring and once in fall. And so we call these lakes dimictic. So to see how these seasonal dynamics play out in an actual lake, I wanted to present you with some real data. So these data were collected from the previous year from Lake Waramaug, which is a lake I think many of you will be familiar with. And so these tables are organized such that you can see changes in the water column through time. So running across the top, you'll see that there's a monthly series of dates. So these profiles were collected once a month. So you can see lake changes from month to month, beginning with April and ending in October. So running down the left-hand side is the depth. So we're looking at the surface of the lake at the top down to the bottom of the lake at 11 meters. Values are color-coded such that high values are in red, low values are in green. And we'll start with lake temperature on the very left. So in April, it's evident that the lake is thoroughly mixed, and this corresponds to the spring turnover condition we talked about in the previous slide. The lake warms up through the summer and begins cooling again until autumn turnover occurs again in September, maybe September to October. So moving on to the middle table, we can see how the temperature profiles relate to lake stratification. And you'll notice RTRM in the title of this table. RTRM stands for relative thermal resistance to mixing. And this is how we measure stratification. So RTRM models strength of thermal stratification based on lake temperature and temperature-dependent water density. So basically, what you need to know here is the higher number represents stronger stratification. So greatest resistance to mixing occurs in summer between the warm upper layers of water and cooler deeper layers of water. And you'll notice that there's no stratification or very little stratification or little resistance to mixing during spring and autumn turnover. Okay, so lastly, I mentioned that stratification of the water column can result in chemical differences between the top and bottom of the lake. And so the last plot on the very right shows that. It's dissolved oxygen in terms of percent saturation. So this is a measurement of how much oxygen is dissolved in the water. So water can hold a certain amount of dissolved gaseous oxygen. This is important for many aquatic organisms which use dissolved oxygen for respiration, just like us, such as fish, for example. So when a lake like Waramaug is strongly stratified, you end up with a situation where there is limited exchange between the top of the lake and the bottom of the lake, and so oxygen can diffuse into the top of the lake from the atmosphere, and it can keep the top of the lake nice and aerated. But since there's limited exchange to the bottom colder layers, due to that thermal stratification, oxygen becomes depleted in the hypolimnion, and it's unable to be replenished from the top. So we're going to be leaving the limnological component of the talk just for now. We're going to move on to discuss climate change, but we'll return to discuss lakes later on in the talk. But for now, we're going to begin by talking about general warming trends in New England. So these are some historical data that I pulled off a website called climatereanalyzer.org. It's associated with the University of Maine's Climate Change Institute. The data that I pulled date back to 1980, though I could have gone much further back in time. But I wanted to discuss recent trends so that we can talk about changes that are relevant to you guys, personally speaking. So perhaps these are changes that you've observed within your lifetime. Certainly these are changes that are relevant to your parents' lifetime, and they're perhaps changes that they've noticed and observed. So on the left-hand side of the slide, the largest graph shows an overall annual average increase in temperature since 1980. The x-axis on the bottom shows years spanning the last 4 decades, and the y-axis on the left-hand side of the graph shows temperature in degrees Celsius, which is the standard unit for measuring temperature in the sciences. And so the blue line represents actual data points within the data sets. You'll see that there's some variation, and so the red line that goes through the blue line is a running average that shows the overall trend. So judging from the red line, we can see that there has been an increase in annual average temperature of 1.25 to 1.5 degrees Celsius. And this may seem like a small value, but understand that that's a significant increase that certainly does have large implications for temperature-sensitive ecosystems, such as lakes and reservoirs. We can also break down this trend into seasons. So we can see how individual seasons are changing over time. And these are depicted on the right-hand side of the slide. The plot titles have 3-month abbreviations. So for instance, DJF and the winter plot stands for December, January, and February. You'll notice that all seasons are exhibiting warmer temperatures, except for springs. Notably, autumn and winter temperatures are increasing the fastest, around 2 degrees Celsius since 1980. Moving on to precipitation trends, the data show that there is a slight increase in total precipitation since 1980. It's about 0.04 meters or 4 centimeters. And so note that total precipitation is going to include snow as well as rainfall. So there's a lot of variation when we break down that annual trend into seasonal components. So data suggests that summer, and especially spring, are becoming slightly drier. And we can also see that precipitation increases the most during winter months, about 5 centimeters or 0.05 meters. Since 1980, data also demonstrate that New England winds have decreased in speed by almost a meter per second. So that's just about 2 miles per hour. Unlike precipitation, which exhibited quite a bit of seasonal variability that we just saw, decreased wind speed is pretty consistent throughout all the seasons. So in addition to the long-term change of climate parameters that we just observed, so temperature, precipitation, and wind speed, climate change is expected to increase the frequency and intensity of extreme weather events. And the mechanism behind this phenomena are complex. It's beyond the scope of this talk, but if you're interested in earth science, earth system science, then I recommend you look it up on your own time because the science behind it is incredible. It's fascinating. But hurricanes are a form of extreme weather events. Since the early 1980s, so lining up with our timeline, hurricane frequency, intensity, and duration have all increased in the North Atlantic Ocean, and this is due to climate warming. This means that hurricanes which hit the southeastern coast are becoming stronger and they're lasting longer. So this allows them to reach ever northwards in their trajectories. So they're regularly hitting states like Maine, New Hampshire, Massachusetts, and Connecticut. So we'll likely see more hurricane-related weather events in Connecticut. And if you were in Connecticut this last summer, then you've already experienced one. Isaias blew through the night of August 4th, I believe, and there wasn't a lot of precipitation associated with this weather event, but the wind speeds were incredible, and they left many trees and power lines down. I lost power for the better part of a week. Similar to other extreme weather events, extreme rain events are becoming more common in New England. So rain events are dropping more rain per event, and their duration is increasing, so they're lasting longer, which is what the graph in the upper left-hand corner is demonstrating. Relatedly to rainfall, the plots on the right are showing trends in flooding. So flooding events are becoming more common in New England. Although it's interesting, despite increasing in frequency, the data in this particular study are showing that the duration and magnitude of flooding events are decreasing. There was a lot of data that we sorted through together, and I just want to quickly recap. In general, we see an annual increase in temperature. This can be split up into seasons, and so we're seeing warmer winters, summers, but especially autumns. When we take a look at precipitation, we see an overall annual increase, but looking at the seasonality, we're looking at wetter winters on average, drier springs and summers, and wetter autumns. Wind speed is consistently decreasing across all seasons. And finally, we are seeing an increased frequency of extreme weather events. So we looked at basic lake behavior throughout the seasons. We considered climate change trends that are occurring in New England. And so now we're going to try to tie this information together to figure out how lakes have been and will continue to respond to climate change. And so I made this cartoon for you guys of a lake to demonstrate. And so we have a basin filled with water, complete with lake sediments on the bottom. It's organized into 3 layers, right? So we have an epilimnion, and the circular arrows within the epilimnion are showing the relative mixing depth. We have a metalimnion, or a thermocline, and a hypolimnion on the bottom. Okay, so back in 1980, we had a scenario, something like the one depicted, where wind speeds were a couple miles per hour faster than they are now. Summer temperatures were on average a degree lower than they are now. And spring and summer precipitation was slightly higher on average. So you were getting flushing of cooler water into the lake. So I don't want to oversimplify things here, but just for the purposes of demonstration, these environmental parameters would have resulted in a situation where lake stratification in this lake would have been reduced compared to present day, right? So lake surface temperature, for one thing, would have been cooler. So this would have resulted in a smaller water density difference from top to bottom. Okay, that means that stratification would have been more diffuse throughout the water column, not as strong. At the same time, you have increased wind speeds, and this would have driven down the depth of circulation at the top of the lake, resulting in a deeper, cooler epilimnion. So again, this would further reduce overall lake stratification structure. And as a result, we can speculate that oxygen would not be depleted on the bottom of the lake because diffusion would be able to occur from the top of the lake to the bottom, right? Because stratification would not be so strong to prevent it. So because water on the bottom of the lake remains aerobic, water quality remains high, all right? We have good water quality within the hypolimnion, and meaning that certain contaminants in lake sediments that can be released into the water during anoxia, so when there is no oxygen on the bottom of the lake, those contaminants instead stay contained within the sediments because, again, we have aerobic hypolimnetic conditions. Fast forward to 2020, summer temperatures are on average a degree higher. Wind speeds are a couple of miles per hour slower compared to 1980. Spring and summers are drier, so delivery of runoff water from the watershed is reduced. And so suddenly we have a situation where the surface of the lake is warmer and the mixing depth of the epilimnion is shallower due to the combined effect of increased temperatures and decreased wind speeds. So this results in greater density differences between the top of the lake compared to the bottom, and that translates into stronger thermal stratification. And because of strong thermal stratification, this lake is resistant to mixing, and diffusion of oxygen into the deep hypolimnion cannot occur. So this results in a condition known as anoxia, which I referred to in the previous slide. And due to some complex reduction oxidation chemistry, nutrients and metals, shown here as P or phosphorus, Fe or iron, and Mn or manganese. So these contaminants that were sequestered away safe and sound in the lake sediments are now released into the water column. Let's not forget that on top of the general climate trends we discussed, there is an increase in the frequency and intensity of extreme weather events. So now we have a situation or scenario where a lake sits relatively stagnant for a long period of time, while phosphorus, iron, and manganese become increasingly concentrated on the bottom of the lake. So If the lake experiences strong enough winds coupled with significant precipitation from an extreme weather event, stratification will be overcome and the lake will mix. And so you'll have a situation where low quality water from the bottom of the lake is now thoroughly mixed throughout the water column. If that lake happens to be your drinking water source, suddenly you may find that your water has an orange or black tinge to it, and that's due to iron and manganese, which are serious problems for water utility companies to deal with. They make for a lot of unhappy customers, as you can imagine. And so, as if that's not bad enough, don't forget about the phosphorus that came out of the sediments during anoxia and is now mixed into the water column. So that phosphorus, which is released from the lake sediments during anoxia, it's an important nutrient for aquatic ecosystems, and it may result in a cyanobacterial bloom. So cyanobacteria are sometimes called blue-green algae. They're photosynthetic microorganisms, and they're becoming an increasing problem in the Northeast United States. So what's so bad about these little guys? Well, for one, they're unsightly, so they tend to be buoyant and they float to the surface and they create these surface scums. They reach high densities. They have this bloom and bust dynamic where one day your lake will be seemingly clear and the next it'll be covered in green. They produce taste and odor compounds. And they produce toxins, and some of these toxins are super potent, right? They kill off livestock, they can kill pets, they can be very harmful to humans. So it's a pretty big deal. So unfortunately, under current climate change trends, New England lake and reservoir conditions are becoming increasingly favorable for cyanobacteria. All right, so conditions that favor cyanobacterial blooms in lakes and reservoirs turns out higher temperatures, solute concentrated water, so water that results, for instance, from warmer, drier summers, intense thermal stratification, which produces still stagnant water at the surface of the lake and also causes the release of iron and phosphorus from the bottom of the lake. They all benefit and favor cyanobacteria. Bacteria are also favored by changing seasonality. So lakes have a natural progression of algae community change throughout the year. And that's what the top panel of this figure is showing. It's displaying cell density of different groups of algae. So cyanobacteria in yellow, greens in green, and diatoms in black. So in early spring, New England lakes will often be diatom dominated. But as the diatom community crashes following the onset of stratification, cyanobacteria, pictured in yellow again, and green algae will compete for dominance. And as winter becomes warmer, lake ice-off is becoming earlier. This means that lake spring season is essentially starting earlier and lasting longer. So cyanobacteria are essentially getting a head start and a longer growing season through the summer, as the bottom panel of this figure demonstrates. Just to bring this all home for you folks, I took this photo from my canoe this past summer in a local Connecticut reservoir not too far away from where I live. The green water is due to an Anabaena bloom. Anabaena is a type of cyanobacteria, pictured in the top right. Other common types of cyanobacteria that I've seen in Connecticut lakes and reservoirs are also pictured beneath it. So this all must seem like a pretty grim scenario and outlook. Our lakes, according to this talk, seem to be in trouble. Yeah, well, yes and no. So I don't want to oversell the concern here. So just as we saw there's variability built into climate trends, there's also variability across New England lake ecosystems. So for every scummy reservoir that I show you, I can also point to a clear low productivity system that does not exhibit the trends that I am talking about in this lecture. So what I'm trying to describe here in this lecture is not so much an acute danger of your lake in your township or municipality is going to turn green next year, but what I'm trying to describe is an overall average long-term trend of lake responses to climate change. With that in mind, we have to wonder what measures are being taken to manage these worrisome trends. What measures are being taken to mitigate the negative impacts that climate change is having on our water quality. And this is surely important for drinking water sources, as you can imagine, but it's also very important for recreational water bodies. There is a growing concern as cyanobacteria blooms grow more frequent and as more research comes out regarding the health effects of cyanobacteria exposure, as well as linking cyanobacteria occurrence to certain environmental changes that are happening, including climate change. So this press release here, pictured in the slide, was issued just a couple months ago, announcing availability of funds in order to address problematic cyanobacteria conditions in Connecticut lakes. The title of the press is a little bit misleading because cyanobacteria are not necessarily invasive species. But regardless, cyanobacteria blooms are specifically called out in this release as a valid concern for funding request. So this is a substantial effort by the state of Connecticut to begin managing cyanobacteria, as well as other invasives, aquatic invasives. It represents about $350,000 worth of funding. So they're taking this seriously. And this funding is open to municipalities, nonprofit organizations, and state agencies. To management of individual lakes and reservoirs, there are a few different options available to the organizations that are responsible for management decisions. So again, these organizations, they could include townships, lake associations, utility companies, or some combination of those. Watershed management is a strategy that reduces nutrients coming from the watershed into a lake. So we discussed a lot of climate change trends today, but another dimension of environmental change that lakes are sensitive to includes human use and impact of the watershed. So this occurs via urbanization or agriculture. And so while watershed management doesn't solve all the problems of climate change impacts on lake and reservoir ecosystems, it can help to reduce lake biological productivity by limiting the amount of nutrients that are entering the lake. So this means that perhaps algae blooms will occur less frequently. Nutrient reduction efforts can be implemented within a lake itself. I explained that phosphorus is an important nutrient that can be released from lake sediments during anoxia. So lake managers can actually use materials with certain chemical properties that adsorb strongly to phosphorus. So they bind phosphorus, preventing its release into the water column. And the most common material is called alum, although there are currently newer products. One is called Phoslock. It's important to realize that application of these treatments are only temporary and they last on the order of years. A rather popular strategy for combating cyanobacterial blooms is the application of algicide. And the most common algicides are copper-based, but more recently they are peroxide-based. So these treatments can be effective, but they do have drawbacks and they don't necessarily address the causes of the algae blooms. Aeration devices, such as the ones deployed in Lake Waramaug and pictured in the slide here, they can be useful in mitigating trends of increased stratification and deep anoxia. So many lake aeration systems exist and their usefulness is going to depend on the particular lake in question and the issues that need to be solved within that lake. But for instance, the lake aerator in Waramaug is a layer aerator. So this manages lake anoxia while maintaining a natural thermal stratification structure. So it doesn't break or degrade thermal stratification. It just slightly reduces it. So it mixes warm oxygenated water from a shallow depth with cold hypolumnetic water from a deep depth. And then it releases this tepid aerated mixture at an intermediate depth. What this does is it preserves lake stratification, as I said, and it maintains aerobic conditions down to a relatively deep depth. So we went through a lot of data, a lot of plots and figures, and I appreciate you staying with me until the end. I apologize that I can't be there in person today, but if you have any questions related to the material we covered, please do be in touch. I love talking limnology, and I consider it a real privilege when I get to chat with young aspiring scientists such as yourselves. So my email is on the cover slide. It's on this last slide here. And again, if you think of something down the road and you want to contact me, get in touch with Kelsey. She'll forward you my email address. Thank you all very much.